Anyone here who's not confident of equations of motion? Questions that you've done so far? Do you feel okay? Are you kind of ready to go forward to learn some more? Because if you are struggling with it so far, you're not in a position to learn more stuff, because then you'll struggle again. So you should make sure that you know what you're doing. Yes?
You have to memorize this.
The equations? Yeah. No, I'll give it to you. I don't expect you to memorize. If that is the only thing that is blocking you from doing the, getting good grades, no, I'll give you the equations. It's not a big deal. But you should know how to use those equations. Yeah.
Did we ever go through page 54, 2 through 6?
We did them all here.
I know, but did we ever go through number, like, I guess we did.
I think we did page 50.
I was working on the first page while we went over the second.
Okay, so you should go through it and see if you are comfortable with it. Now, if you feel that you are not comfortable so far, the reasons could be: one, you were physically here, but not mentally here, which means you're kind of sleepy. And then you wake up and take some notes, again sleepy. You're missing a lot of stuff. Because 99% of learning physics takes place in the classroom. I told you this earlier. That's one reason. Second reason, you paid attention, but you didn't take notes. So there's nothing for you to kind of review. How long is it going to stay in your head, whatever you understood? You understood 100%. But after a couple of days, they'll all be gone. They'll all be gone. See, it won't stay in your memory. And I think it'll stay in your memory unless you kind of brush it again and again. Like if I ask you, what did you take for breakfast on October 1st? Then you're like, what did I take for breakfast? I forgot. You're supposed to forget. You're not supposed to keep that in your head. Now, if you really wanted to, remember that, what do? You took a breakfast on October 1st and you say, all right, somebody may ask me this anytime, so I better double check. So after 2 days, what did I take October? Oh, I took this. Okay. After 2 days, check it again. Check it again. And even if it is December, you will know exactly what you took October 1st. Because you're reviewing it. You know what I'm saying? So that's the third component. Having good notes in the book is not enough. I told you this, at least 5 minutes. Spend at least 5 minutes at home flipping through the pages of your notes, trying to find out what you have done so far and where we are heading to. If you don't do your homework, you're not going to do well. Footballers know that, right?
Yeah.
Before your game, you have to do your homework. You've got to study the opponents and really study. Make sure that you know where you're heading to. Not like blindly going there and then just facing all the trouble. You have to study yourself and others, and then you know exactly whose weak points are there. Okay, so if you keep these three components properly intact and follow my instructions, you will have absolutely no problems with physics. You'll be successful. Anyway, we are going to go on. So what we have done so far is motion, which is horizontal, like a car starts off from rest and then accelerates and moves a certain displacement and then comes backward and whatever, like those kind of problems. And what we are going to do today, primarily, is about vertical motion. How is it going to be different if it is vertical? Now, vertical motion can be two types. One is this type of motion where an object starts like a rocket, which is propelled by the exhaust gases. So the rocket starts from here, accelerates upwards, goes faster, 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 faster. That's one kind. And the other kind of problem is this. Something which is tossed is going to experience a kind of motion which is controlled by what?
Gravity.
Gravity. Nothing else controls it. Only gravity controls it. And gravity acts which way? Downward. So this object is going to suffer a force of gravity, and because it's suffering a force of gravity in this direction, it's going to experience an acceleration in which direction? Now, anything that is acted on only by gravity is called free fall. That's called free fall. So what is free fall? Anything where only one force is acting on it, which is its own weight. Gravity. Now look at this marker. Is gravity acting on it?
No. Yeah.
No. Gravity acts on everything. The force of gravity acts on everything, everywhere. So is this marker acted on by gravity? Yes. But is there anything else acting on it right now? My hand pushing it up. So now two forces are acting on it. And that is why this is not free fall. When is it free fall? That's free fall. When only one force is acting on it, which is this.
Is it still free fall if it's like air resistance?
Oh no.
It won't be free fall then?
No. So when I jumped off the airplane, I experienced free fall that few seconds. That is free fall. Why? Because the only force acting on me is my own weight, and so I was accelerating downward. But very soon I start getting hit by air resistance, which is an extra force coming upward, and that keeps growing. And because it keeps growing, my acceleration will reduce, and finally my acceleration becomes zero. And from that moment, I cruise at a constant velocity of 140 miles per hour. I won't speed up anymore because there's no more acceleration. Do you understand what I'm saying? Initially, the acceleration is there, maximum. And after that, once I reach that speed of 140 miles per hour, then I'm not accelerating anymore. Why? Because the net force is zero. The weight is acting down, yes. That means the earth is pulling me down, and the air resistance is pushing me up the same way. Got it? I don't know if you got it. Hudson? Got it? What about you? I don't know. I don't believe you got it, but I'll just go on. I told this very clearly. 3 things that can go wrong in your learning physics. 1, sleep during class. 2, not taking good notes. 3, not reviewing the material sufficiently. If any of these are your habits, if any of these you don't follow, then the problem is going to happen there. And it'll be too late if you actually wait for a couple of weeks, then it'll be too late, because then there'll be so many things you don't understand, and therefore it is difficult to learn. I've told this from the first day. Physics learning is like climbing a ladder. You have to be grasping each and every step, and then you will be feeling absolutely confident. Anyway, I won't be reminding again and again. So, you know what is free fall now? Right, Jacob? What's free fall? Only one force is acting on it. And when only one force is acting on it, the acceleration is downward. And this acceleration is called acceleration of free fall, which is negative 9.8 meters per second squared, or negative 9.81 meters per second squared, or negative 10 meters per second squared. It depends on what is required. If you're looking for 2 sig figs, then it is this. If you're looking for 3 sig figs, then this is this. If you're looking for 1 sig fig, then 10 is fine. Yeah.
That's the same for any object,
Any object,
no matter like the weight.
no matter the weight. For any object, the acceleration downward initially is negative 9.8. Yes.
Would it differ, like, if the shape of it is different?
No.
Would it differ if it's on another planet?
Oh, yes.
So wait, like, if it was designed to, like, cut through the air and go as straight down as fast as possible, it would have been different.
That's why I mentioned this. Initial acceleration is negative 9.8. I'm not guaranteeing what happens later.
Right, because it's not free fall. It's
Yeah.
air resistance.
If the air resistance comes into play, it's no more free fall. That's why I'm saying clearly acceleration of free fall, assuming it's in space. Yeah.
Is there like a scientific name for like all the planets' gravity? Like, I know how you say it's just gravity is 9.81 meters per second, but like, is there a scientific name for Earth's gravity? Because all planets have different ones.
Well, I think it's like the kind of G, right?
That is the G, yeah.
Would you just say Earth's gravity is?
Yeah, the Earth. This is for the Earth. Now
Well,
this
what
is
if we're on a different planet?
no, this is only for Earth. This is only for Earth, and that too ground level. This is not everywhere. This is not everywhere. Yeah.
If someone's 200 pounds jumps out of a plane and someone's 100 pounds jumps out of a plane, will they hit the ground at the same time?
No, initially they'll both be accelerated together. But what happens is the 200-pound person must be obviously bigger, so he'll suffer more air resistance.
Okay.
But his weight is more, so there's a kind of balance that takes place there. Ultimately, the lighter one, whose surface area is not greatly different from the heavier one, will suffer more air resistance quickly, and so will start reaching the terminal speed earlier. So if a lighter person goes down, he will reach a terminal speed of probably 100 miles per hour, whereas a heavier person will go to 150 miles per hour. Depends.
Yeah.
And the surface area is a very important thing. So even in the air, when you're falling freely, when I'm going at 140 miles per hour, if I want to go faster, I just cuddle up into a ball and I'm like going down faster. Or if I just aim myself not like this, but instead point your hands down and go down like this, then you can cut through and go faster than that. Yeah, that's how they can control the speeds themselves, by just bundling up, going flat. That's why most of them are actually doing this, because they want to just resist more. Yeah.
From the second, like, say you jump out of a plane, aren't you always experiencing air resistance?
No, not at that time.
Why not?
Oh, you mean the forward air resistance?
Yeah.
Yeah, that is there, but downward air resistance, no.
So if air resistance wasn't a thing, a feather in like a car would fall at the same speed.
Absolutely.
Didn't they like test that on the moon?
Well, you can test it even right here. I don't have the right gadgets here, but there's a glass tube. Okay, there's a glass tube which can be connected to a vacuum pump. And what's inside the glass tube is one feather and a penny. Okay, so when I don't connect it to the vacuum tube, if the feather and the coin are here, so all of a sudden, if I just flip like this, you will see the coin kind of rushes down, and the feather like comes down slowly. Then connect to the vacuum pump, suck the air out completely as much as possible, seal it again. Now when I flip it, the feather and the coin come together. Unbelievable, but that's what happens. The feather and the coin both will suffer the same acceleration, and so they will both gain the same speeds, and so they'll go together. Yeah.
That's what they did on the moon landing, right?
Yeah, they did that for sure.
Yeah.
Right. So, do objects that experience free fall ever reach terminal velocity, or are they always accelerating the same amount?
If there is no air resistance, they will keep accelerating. So basically, if you jump out from space, you're going to speed up really bad.
Like a meteor? Just
Like a meteor,
example.
basically. You'll speed up so much that once you enter the Earth's atmosphere at those speeds, the air resistance will start like rubbing on you so much and heating you up and burning you up. Finish. You'll just be another meteor. Gone. One spark. That's what happens. Yeah, but if you have some method of resisting slowly as you enter the Earth's atmosphere, if you slowly start, controlling your speeds and all that, you can actually apply brakes, and then later on apply more parachute and stuff like that and slow down. Yeah.
Isn't there a guy who jumped from space down to Earth?
It was like on the.
To break the speed of sound barrier, that guy?
Yeah.
Yeah, he had to go really high and
Should
jump
try
from.
that, Mr. Sam.
I don't mind.
You'd like catch on fire.
No, when there's no air resistance, you're actually like going super fast.
Then you hit the air. And it's
No, you don't hit the air all of a sudden. It's not like hitting water. Air becomes it's like when you enter the Earth's atmosphere, it'll be like few atoms, one there, one there, one there. And as you go down, it'll become more crowded and more crowded and more crowded. The most crowd is here. That's why you get more air resistance when you get close. So these cars are actually having more air resistance. So a plane, when it takes off, has much more air resistance than when it is at 35,000 feet. The very reason why it's going to that height to fly is because it wants to fight less air resistance so that it can fly faster. That's the whole goal, right?
Is that why when it flies lower, you get more turbulence?
Yeah. So once you're lower, it is thicker air. And once it is thicker air, depending on the wind and all those things, it can cause more turbulence. Yeah. So when it comes down to land, it has to reduce the speed. When it's flying at 35,000 feet, it is probably flying at 350 or 400 knots. But you can't land at that speed. Or you can't enter the Earth's atmosphere. Like, you can't come to ground level at those speeds. It'll damage all the parts. So before they come down, they have to cut down the speeds slowly. And then before, like almost 10 miles before landing, their speeds are like 200 knots. And then they cut it down further. And as they are touching down, it'll be like 150 knots. They have to cut it down. Otherwise, even with the wheels like that, without removing the wheels, without what do you call that? If the wheels are still outside and you fly faster, it can really cause problems to the wheels. You can have the wheels landing gear damage. The same with the flaps. If you keep the flaps and you fly faster and faster, the flaps can get damaged. Yeah.
All the wheels just like revolve at a certain speed.
Yeah, it can revolve, but more than revolving, there are so many things that are mechanically there which can get a lot of shear and it can damage. All right. I know there are plenty of questions about so many things, but yes. So acceleration due to gravity on the Earth's surface is negative 9.8 meters per second square. Is that clear, Hudson? What happens if you go into the Earth? Like if you dig a hole and start going inside, the acceleration due to gravity becomes lower. And what if you go right to the center of the Earth? Acceleration due to gravity is zero. Basically, you can float there. You can float there because you don't have anywhere to go. Nothing is pulling you.
It's like a field trip.
One-way field trip, right?
Magic school bus.
So, at the center of the Earth, there's nothing pulling you. I mean, like everything is pulling you. Like this part of the Earth is pulling you this way, this part of the Earth is pulling you this way, so you have nowhere to go.
It's not like you're floating, it's like you're being crushed.
No, you're not crushed.
Ripped?
Like you're ripped out, basically.
Ripped.
See,
Not too much, though. It's not like too much force acting on you.
you wouldn't die. That's the heat. Like,
Yeah.
Is that like, well, you would have to die because the entire weight of the Earth is like on top of you.
No.
When you're like in the middle of it.
Like you're like a bubble. It's like
No. Imagine you make a hole all the way down to the other side of the Earth. and you go down, and assume there's no heat component and there's no air resistance, nothing, and if you drop yourself there, you'll be like accelerating at negative 9.8 first, and then after that slowly kind of reduce to negative 8, negative 7, negative 5, and when you reach the center of the earth, it is 0, but you're going too fast, right? So therefore you keep going to the other side and slow down. And by the time you reach the other side, you'll return back. So you'll keep doing this.
We'll go home and start digging a hole.
To China?
Yeah.
Practical advantage.
Okay. So you understand the main idea there. So gravity, acceleration due to gravity keeps going down as you go. Now what happens if you go above the Earth's surface? Same story. So that's the Earth. How far are we from the center?
Pretty far.
Pretty far. 4,000 miles only.
That's it.
So 4,000 miles from the center of the Earth. And we are here. What's the acceleration? Negative, let's say 10. So right now on the surface of the Earth is negative 10. If you go another 4,000 miles, it is negative 2.5. It drops like that. So if you go 4,000 miles upward, the gravity drops to 2.5. So if you consider flying in the plane, which is actually flying at 5 miles or something, it's nothing at all. So is the acceleration due to gravity at the plane's height lower than here? Yes, but not significantly low that you will notice. You don't, yeah,
Is the gravity at the surface, is that the strongest it gets?
strongest. Gravity at the surface of every planet is the strongest. If you go down or if you go up, it's going to reduce. Okay? So you understand something about free fall. Good. Now you're going to do some stuff. Acceleration is downward, right? Always, always. On any planet. So even if I tell you, take the acceleration as 5 meters per second squared, you have to take it as negative 5 because you know it's always downward. All right, now an exercise here. I want you to draw a graph. I want you to draw a graph of velocity time. Now remember, all these quantities are vector quantities, right? So initial velocity, final velocity, displacements, all these are vector quantities. And so you got to be careful because you got to use the proper sign conventions. Okay, here is the situation. I'm taking this marker and I'm tossing the marker up. So watch what I'm doing. I toss the marker up and the marker came back to my hands. Got it? I tossed the marker up, the marker came back to my hands. Can you draw a velocity time graph for that? I'll give you some time. Draw a velocity time graph of that. No need for numbers, but just the sketch of how it will look like. And do it with pencil so you can always correct it. Anybody needs a pencil? Good catch. Yeah. Make a sketch and then I'll come and have a look at it. I see most of you have drawn this, right? I see most of you have drawn this, or slightly curved.
Yeah, we did
Okay.
No.
Let me explain to you what this is. What's the initial velocity?
0.
Which means you're saying the marker left my hand at 0 velocity. And then it started picking up velocities. It started going faster and faster, like a rocket.
Using force.
What for? It's in the air. Free fall. It's free fall. Once it leaves my hand, I'm not controlling. What's controlling it? Pulling which way? And it goes faster and faster like this? That's not possible. I know why this mistake happens, because you are totally confused. You see the marker is at rest in my hand and then I throw it, right? The problem is because you have a little bit of clarity issue on what is the meaning of initial velocity and what is the meaning of final velocity. Can you write it down? Initial velocity. Can you write down? Initial velocity, write this whole statement. Initial velocity is the velocity, initial velocity is the velocity of an object just after it starts the journey. Initial velocity is the velocity of the object just after it starts the journey. And then write about final velocity. What is considered to be a final velocity? It is the velocity of the object just before the journey ends. Just before the journey ends. Got it? So if someone actually is firing a bullet into the air, what's the initial velocity of the bullet? Well, remember the bullet was at rest in the gun. So do you take it as 0? No. The initial velocity of the bullet is taken as the velocity with which it leaves the gun. Starts the journey. The same way final velocity. For example, the quarterback throws the ball at goal. And he's catching the ball. At what speed, at what velocity did the ball strike his hands? At what velocity did the ball strike his hands? 0? Because he catches the ball and brings it to rest. It's not 0. It is the velocity just before he touches the ball. Like at what speed, velocity did it just reach his hands? That is the final velocity. After catching the ball, he's putting in his pocket. I mean, that's not our business. The story ends over there. So the story starts immediately after, and story ends immediately before. Before finishing. So this marker, of course, the final velocity seems to be 0, but that's not final velocity. What's final velocity? It's the velocity with which it comes and hits my hand. That velocity. That velocity. Because after it comes and hits my hand, it's going to my pocket, but that's not part of the problem. Do you understand this? So, this graph is definitely not right. And watch again. I'm throwing the marker upward. So when it leaves my hand, it is going upward. So let's put some numbers. I'm throwing it at 10 meters per second. So the initial velocity is positive 10. And then what happens to the velocity? Will it stay positive 10? It'll become positive 9, positive 8, positive 7. 6, 5, 4, 3, 2. So the graph starts here. Is that clear? It's not starting here, it starts there. What happens to that? From here, is it supposed to come down? Yes. But is it coming down in a straight line or a curve?
Curve. Well, no, it's like that. Right?
Why?
Accelerating. Because
What kind of acceleration?
it's free fall.
It's like a constant
Gravity.
Constant acceleration. The acceleration is constant. Uniform acceleration. How do you draw uniform acceleration on a graph? This one, straight line. It's a straight line. So where is this point? What is that? What is this? What is happening here?
That's when it reaches the top.
That's when it reaches the highest point. This is when it reaches the highest point. So that highest point. Now continue the graph. See? Continue the graph. Complete the rest of the graph, and I'll tell you what the meaning is. Again, I see some of you drawing this. I see some of you drawing that. I'll tell you what this one means. This means it starts at positive 10. Watch. 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. And then 1, 2, 3, 4, 5. So the marker went slowing down, stopped, and starts again, which is not practical. So this line is impossible. That's not what's happening. So what's happening now?
Isn't it going mad?
Yeah, it continues down. It continues down. Correct. So, what is the slope of velocity time graph? What is supposed to be the slope of velocity time graph? Slope of velocity time graph. Acceleration. So the acceleration, look at this. It's pointing down. So what kind of acceleration is this? Negative. Negative 9.8. So slope of this line is negative 9.8. Slope of this line, negative 9.8, negative 9.8, negative 9.8, negative 9.8, negative 9.8. Everywhere. Because what is controlling it is the Earth. So the graph is a straight line and the slope is constant. This clear? Yes? Okay. Now answer my question once again. Watch what I'm doing again. I throw this marker, goes to the top and returns back, right? At the top, where the velocity is 0, what is its acceleration? At the point it was turning around, what is the acceleration at that topmost point?
0. It's the same 9.8.
It's the same, negative 9.8. Slope is the same. Look at the slope here. So don't make mistakes like that. I said what?
Always.
Just because it momentarily stopped does not mean Earth has stopped pulling it. Earth is still pulling, that's why it turned around. It makes sense? It's a very common mistake, that's why I'm pointing it out. Many people actually make a mistake. They'll fall into this blunder. At the topmost point, when the velocity is 0, what is its acceleration? Or if I give you a question saying, whenever the velocity is 0, the acceleration has to be 0. No, not necessarily. Not necessarily. Acceleration can still be there. Proof. Okay. Now, more info. Yes.
How do we know that it stopped? Going back down.
Oh, I'm going to explain. What does the area of a graph represent? Displacement. So what is the area of this triangle? What does it tell you?
How far it was until it reached the point.
How far it is till it reaches the topmost point. Do you get it? How high it went. That's what it is. How high it went is the area of this graph. Now what about the area of this part? What does that represent?
Negative displacement.
How far it went? Down. You got it? How far it went down. That's what this one represents. So this is a positive area. This is a negative area. What's the total area? 0. Why? Because the total displacement is? Because it went off from my hands and came back to my hands. Net displacement is 0. Does it make sense? Hudson? Huds? Your pencil is not doing anything useful. Okay. Give some work for the pencil. Yeah.
I mean, doesn't like the negative and positive cancel each other out?
That is what we are talking about. Why the negative and positive cancel each other out? Because the overall displacement is 0. The marker was in my hands. Now it's back to my hands.
What if we dropped off the building?
Yeah.
You're thinking one step ahead of me, that's why. Okay, now watch the same scenario. Look, I'm dropping the marker. I'm throwing the marker up. Watch this. I didn't catch it. I missed the catch. Went down there. How is the graph going to be different?
It would be longer on the bottom.
That's it. It will be longer in the bottom. So the area of this part will be bigger. So what is the overall area? Negative. Which means the overall displacement is?
Negative.
So it started off in my hands here, but it ended down there. That's what this shows. That was your question, right? So, is it clear? All right. You take this off. So the slope of the graph has to be that, and the area is supposed to be the displacement. Now, here's a problem for you. Now we're starting the problem solving. Suppose I take a steel ball, open the window, hold my hand outside, and drop the steel ball. I just dropped the steel ball. And let's say the height of this is 20 meters. How long did it take to hit somebody, or how long did it take to hit the ground?
2 seconds. Yeah, around 2 seconds.
What do you do? Do you just give a guess?
2.875.
You record
Negative 2 seconds.
What do you do? How do you solve problems?
You
You write down the diagram.
Before that,
You draw a diagram.
draw a diagram. Okay, so here is the ball, a steel ball. Now why I chose steel ball is because it will be small and smooth and it will have less air resistance and more weight. That's why. So this ball is dropped and it hits the ground here. The height is 20.0 meters. Pay attention to every little detail. This is a story. My question is, how long did it take? So we drew the diagram. What do you do next?
You equation.
Before equations.
You plug in your numbers.
Make a list of what you know.
Your variables?
Variables. What is initial velocity? Do you know anything about it?
9 point.
I dropped the steel ball.
Oh, 9.8.
Oh, negative.
I didn't throw the steel
Starts at
ball.
0.
I didn't throw the steel ball. I dropped the steel ball.
It starts at 0.
When you see the word dropped, dropped means just releasing it from rest. That's it. You're not imparting a velocity to it. Make sense? What else do we know? Acceleration, how much?
9.8. Negative 9.
And what else do we know?
The final.
We don't have any clue. Final loss, we don't have any clue.
20 meters.
We have what? What is that called?
Distance.
Displacement. So what is the displacement?
20.0.
What is the displacement?
Negative 20.
Negative 20.0. Watch out for every little thing. So when you discuss about the displacement, what do you say is, okay, it was here, now it is here, it's below. And so you have to put this minus sign. Nobody's going to give you these minus signs. You have to put it. Because you know it's going below. And what is my question? Time. What is the missing variable here?
Final.
So which equation do you use? The one without final velocity. Take it. What's the equation without final velocity? All these equations must be at the top of your
X
thoughts.
equals initial velocity times time plus 1/2 acceleration times squared.
Alright, so we got the equation. Now comes substitution. So just faithfully substitute stuff. Since the initial velocity is 0, VIT is going to be 0 anyway, right? So initial velocity 0 solves a lot of issues because it's mathematically much simpler. See? VIT is completely out. Anything multiplied by 0 is 0. And then on this side we have negative 9.81 times t squared. Up to here the physics part is over. Now from here is the mathematical part of it. What do you do from here? Multiple ways of going forward. We can multiply the whole equation with 2, or you can just do this. You can do that because this is half of 9.81. See? So when you say half of 9.81, you just divide this with 2. So you got that. What do you do from there onwards? T squared is equal to negative 20.0 divided by negative 4.905. So whatever answer you get for that is t squared. And then what do you do to get t? Square root it. So square root the answer here, it will get you the answer. So tell me the answer now. Exact to 3 sig pigs. The calculator must be on.
$2.02.
2.02 seconds. Yeah, so in reality it will take 2.02 seconds. And that is assuming air resistance is not in the picture. That's why I took a steel ball. If you take a ping pong ball, it's definitely going to take more time than this.
Is there like an equation for air?
There are equations, but it's not right now. Not right now. I don't think you will be dealing with air resistance at all. We'll discuss qualitatively about it, but not quantitatively. So if it was a ping pong ball, it would have taken more time because the air resistance will act more severely on a ping pong ball than on a steel ball. It's like, you know those water slides? You know the water slides? Now think of a heavy person on the water slide. And the next slide, there's a light skinny boy. What happens, the skinny boy gets stuck halfway down. Like, you know, he's not able to move, then he has to pull himself out. Because the friction between his legs and the slide kind of stops him. So he has to physically pull himself. What about the heavier part? That's it. Once he's down, no stop, he goes crashing down. Yeah, because yes, there is resistance, but his weight is much more. So he goes pretty fast. And he lands pretty fast too. So everything, you know those spiral water slides, have you seen that? You get inside and then you go into a bowl and then you kind of spin around. I've seen, I've not been there, but I've seen from outside like what's going on, and I can see like very clearly the lighter ones like one turn and then they're down inside. That's it. They're stopped so easily. But the heavier ones go for a good spin. They don't stop that soon. And then they go down. Alright, so, yeah. Now, if the question was not asking for time, but if I asked you, what is the velocity with which it hits the ground? Obviously, the steel ball is going to come to rest. But that is not our final velocity. What's the final velocity? It's the velocity with which it hits the ground. This one. So if I want to find out final velocity but not time, what equation will you use? Cole? What equation will you use to find final velocity?
VI equals AC.
Assuming we don't have time now.
We don't have time.
We don't have time.
VF squared is equals 2AX plus
Vf square is equal to Vi square plus 2Ax. Now substitute. So Vf square is equal to, that is 0. Because the initial velocity is 0, it's out of the picture. 2 times negative 9.81 times negative 20. Now use your calculators. This whole thing will turn out 392.4. So you find the square root of that number, and that will be the answer. What's the answer? Let me see if you are sharp enough to give me the right answer.
19.80.
19.8 is close.
19.80.
No,
19.81.
3 sig figs are enough.
Three.
3 sig figs. 3 sig figs.
Oh, that had 4 sig. Oh, 19.
No, this is, you don't worry about sig figs on this.
Oh.
You worry about sig figs in the given quantities.
Okay, so 19.8. Negative 19.9.
Huh?
Negative 19.
Negative, see, when you said a positive number, it means that it is going up when it hit the ground. Is it? So how come it becomes negative? When you take the square root of any number, you have two answer choices. You have two answer choices. Whenever you take square root of any number, you have two answer possibilities. One is positive and the other is. And in this scenario, what will you take as the final answer? Is that clear? Clear? All right. Okay, now take another problem. Cole, how fast can you throw a football?
60 miles an hour.
Upward.
Oh yeah, probably upward like 80.
Faster? I thought it was going to be slower.
Let's just say 20. 20 on a bad day.
Let's say 25. So let's see. Cole, write it down. Cole throws a football vertically up. Cole throws a football vertically up at 25 miles per hour. No, sorry, meters per second. 25 meters per second is like 55 miles per hour on a good day for Cole. Right? So he throws a football at 25 meters per second, vertically up. Question is, how long does it take for the football to reach back into his hands? That's a question. Write it down. How long does it take the football to return to his hands? So Cole throws a football vertically up at 25 meters per second. How long does it take for the football to reach his hands? So what do you do first? Draw a diagram. Okay? Don't forget those steps. If you forget some steps, you're in for difficulties. If you make those steps properly, alright, so here is the football and he's throwing it up at 25 meters per second. And then what do you do?
Is it not squared? That 25 meters per second?
No, 25,
Oh, no, wait.
25 meters per second. It's not acceleration, velocity. So what happens to the football after it's thrown? It goes up, goes to the top, takes a turn, comes back into his hands. So that's the picture. Now what do you do next? Diagram is already here. What is
What you know?
what do you know? Yes, what do you know initial velocity is? 25 meters per second, positive, because it's upward. What else do you know? Acceleration. And what else do you know? The question is, what is time? Huh? I don't have final velocity.
Wouldn't it be 25 meters per second?
It won't be.
Uh,
In
no.
reality, it will be negative 25, but assume we don't know that. You can't take for granted certain things. In physics, if you're given something, take it. You can't just assume something.
Displacement.
What is displacement?
0.
Huh?
0.
0!
Oh yeah.
Because it returned back to his hands. Watch the football. Goes up, comes back to his hands. So it is no displacement, net. And the question is how long? So what equation?
The one that doesn't have final velocity.
That's right. So x is equals to VIT plus half AT squared. Now substitution. 0 equal to 25t plus 1/2 negative 9.81 t squared. As I said, the physics part is already over. The rest of it is your algebraic skill. I'll give you some time. Go ahead and do what you can there. Yeah.
5.1.
5.1 is the absolute answer. Correct. Now, mathematically, some of you are struggling. Let me help you out there. What did you do from this step onwards? From here?
Oh, I know.
What do you do?
I just substitute everything in.
What?
So
So
multiply 1/2 negative 9.81.
you can do that. So it becomes 0 equals 25t minus 4.905 t squared. What can you do from here?
You can divide t. So you can subtract.
You can do that. Or subtract. Subtract 25 from both sides, 25t from both sides. So you have negative 25t equals negative 4.905 t squared. What do you do from now?
Divide by, or
Yeah, you're right.
yeah, divide by negative 4.905.
No, divide by t. Because you see t on this side and t on that side. So you can divide by t on both sides. So this is gone. And this 1t is gone. What is left now is negative 25 is equal to negative 4.905t. So the answer for time is negative 25 divided by negative 4.905, and the answer is 5.1 seconds. So it takes 5.1 seconds to reach his hands. So imagine, look at the clock. Imagine he's going to throw right now. It's already gone. Reached. It's coming back, and got. So that much time it takes. So it takes 5.1 seconds. So after he throws the ball, he can just spend 5 seconds exactly and then look up and catch. Exactly. Alright, so we're solving problems, we're solving puzzles. How long it is in the air, that's what it is. Now on page 60, go to textbook. Go to your textbook. On page 60, there are 4 questions. You should be in a position to do all of them without any issues. But go to the first question and answer it right now. 60. Page 60, the first question. You must be able to easily answer that question. Always follow the steps. Draw a diagram. Write down the variables given. Put a question mark on the variable that you want to find out. Identify the missing variable. Then choose the appropriate equation. So do 1A first. If someone has an answer, let me know. And let those who are absent know that this video of this class will be on Rockspace under class videos. Yeah.
I have 42.1 meters per second.
You want to refine your answer a little more?
Negative 42.
Negative 42, that's correct. So since it is Mars, you use the acceleration due to gravity for Mars, but it will still be negative. So the camera falls 239 meters, and you want to know how fast it's coming and hitting the ground. Given initial velocity is acceleration negative 3.7, displacement
Is it negative 230?
negative 239, and the question is asking for final velocity. So time is absolutely out of the picture. So we use the equation and then substitution. Vi square is 0. And then you take the square root and choose the appropriate sign. Yeah.
Whenever you have 0, you wouldn't account for like the sig things of 0, right?
No.
Just like one.
No. When it's 0, 0, 0. So you should get negative 42 meters per second. Obviously, when you take the square root, you'll have two answers, positive 42 and negative 42. You have to choose whichever is appropriate. In this case, it is on its way down, and so you choose negative 42. Does it make sense now? So you have an idea about free falling motion, equations of motion? To some extent, we'll do more work as we go on.